Good morning, ladies and gentlemen. It's PMC pleasure to have you again on the pre-training presentation. And as you all aware that this week is the second block for mechanical equipment. We talked last time about heat exchanger level 1, and this week we're going to talk about reboilers and condensers. I will hand over to Olga to take us through the slides for today. Thanks for everyone attending the session, and thanks for Olga.
Hello, everybody. Thank you, Amit. Welcome to the Reboilers and Condensers session. Today is the first part. So let's gonna start. First, we're gonna start with the safety moment. I have chosen also a safety moment related with heat exchangers with an accident occurred in Australia related with a heat exchanger. That was at Longford near Sale in Victoria in Australia at ESO plant. That processes crude oil and raw gas from Bass Strait offshore oil fields. Yes. The site comprises all these areas. The first one, the crude stabilization plant. And also we have 3 gas plants, GP1, 2, and 3. The GP1 is refrigerated by lean oil absorption plant, and GP2 and GP3 are cryogenic separation plants. So what happened the day of the accident? On Friday 25 of September in 1998, an explosion and fire that burned for more than 2 days occurred at the ESO Longford facility in South Gippsland in Victoria. As a result of that explosion and fire, 2 people were dead and 8 were seriously injured. Also, all natural gas supply from the Longford facilities ceased, causing major disruption to Melbourne industry and retail consumers. And why happened this accident? Well, the deethanizer reboiler, the one you see here, the GP905, the shell temperature fell from 100 degrees to minus 48 degrees due to an accumulation of other plant malfunctions that occurred before, and they did not notice. So then, due to this shell temperature fall, an ice was formed on uninsulated surfaces of the reboiler. The GP1201, the pump that started the plant, this pump restarted and warm lean oil flow resumed to GP905. After restarting the plant, the reboiler still became brittle, and thermal stress generated by radial expansion of the tube sheet created a stress that resulted in brittle fracture. So the consequences of this break due to this thermal stress on the tube sheet were that vapor cloud containing flammable gas ignited, resulting in an intense jet fire beneath elevated pipe rack junction. Also, they were unable to isolate leak, and flame impeachment caused 3 more leaks. Due to that, the entire plant inventory was lost, and fire burned for more than 2 days. and finally, and the more catastrophic and fatal consequence were that 2 people were dead and 8 injured. So after this accident, the Royal Commission did a study, and they found the following findings. They state that the accident was the result of having an inadequate personal training and lack of operating procedures. Also, they had an excessive alarm and warning systems that caused that workers were used to these alarms, so then they became desensitized to possible hazardous occurrences. Also, they had poor communication between shifts, meant some previous malfunctions were not communicated to the following shift. Also, the company did not perform HAZOP analysis, safety analysis, of the heat exchange system, which would have highlighted the risk of tank rupture caused by sudden temperature change. And finally, company's safety culture was more oriented towards preventing lost time due to accidents and injuries, rather than workers' protection and health. So after these findings from the Royal Commission, the following recommendations were performed. The first one, they recommend that all major hazard facility sites shall have the safety case extended to them by legislation. Also, they recommended to have a design review of critical facility areas to minimize the risk of serious accident, including an isolation philosophy. They also recommend to have periodical review of operating standards and practices and the training of employees in identifiable hazards and the procedures to deal with them. And finally, they recommend a safety and risk assessment and the responses required to minimize likelihood of accident, including fire risk analysis and emergency response. So for me, this safety moment was very interesting because it was an accident caused by, as we said, by one of the reasons were that there were some malfunctions before the accident that were now noticed by the workers. So this is typical in many industries. This is a typical reason for major disasters and major fatal errors. And the findings performed by the Royal Commission are 5 typical findings, 5 typical acts that usually happen and usually happen in all the accidents. So this is very important to keep these 5 findings in our heads and also in our safety culture.
Yeah, I just want to comment on the safety moment.
Yes.
We talked a bit in Arabic. شباب يعني إن شاء الله باكر عقبه من تستلمون مسؤوليات بالتشغيل النقاط اللي سببت أدت إلى الانفجار بالغاز بلانت هذه راح انتم تشهدوها يعني on daily basis هاي الاكتيفيتيز. فدائما تخلون ببالكم شنو الاشياء البسيطه اللي ممكن واحد يهملها بالعمل اليومي تؤدي الى ديزاستر. فطبعا واحده منها اللي هو اول نقطه مثل ما تشوفون inadequate personal training او lack of operating procedure. يعني انت كل خطوه عندك تريد تأديها بالبلانت او باليونت لازم انت تشتغل ضمن بروسيجر، يعني مو رندم، حتى لو انت فاهمها 100% كل الخطوات، بس هي تكون مكتوبه. ليش؟ لانه انت راح يكون عندك سيستم تشتغل عليه، بحيث انت يعني تتلافى اي خطا ممكن يحدث اثناء الاكشن للمشغل او للمينتنس. النقطه الثانيه اللي هي كلش مهمه اتصورها، هذه اللي هي excessive alarm and warning systems caused workers to become desensitized to possible hazardous occurrences. هذه اللي ما كانت واضحه الى النقطه، واحنا شايفيها باثناء التشغيل. من تصير عندك الارمات كثيره بداخل غرفه السيطره وتسوي لها اكنولج بحيث حتى يسكت الضوضاء او ضوضاء الالار، وتعرف تقول اوكي هاي المشكله مو حرجه، وهذا بيه مشكله دائما، فمثلا افرض يعطي الارم، بس لكثرتها الموجوده في هذا الحدث اللي صار اكو عندهم تعود على الالارمات، بحيث ما يروحون فعلا يحلون المشكله. وحتى اذا هي المشكله ثانويه انت هم لازم تاخذ اكشن وتحلها. فقاموا شو يسوون؟ مجرد يسكتون الالارم بس ما يحلون اصل المشكله. ولكثرتها فصار اهمال، بحيث تقدر ما تميز بين من هو الكريتيكال ومن هو السكندري مثلا الارم. فهذه مهمه، انه انت من يصير عندك هيك موقف دائما انت تاخذ البروبر اكشن، بحيث انت يو افويد يعني such ديزاستر. لانه انت تخسر الوحده وتخسر حياه ناس، وقد تخسر المعدات الموجوده بالوحده، فالدمج كبير يعني، اضافه الى انه تخاطر في حياتك وحياه زملائك بالعمل. البور كوميونيكيشن، من يتغير الشفت لازم انت النوتس مالتك تكون واضحه، لغتها واضحه، كتابه واضحه، التسليم اذا حتى عندك يعني كوميونيكيشن فيربال كوميونيكيشن بالكلام، هذه هم لازم تكون جدا واضحه، بحيث انت ما يصير بور كوميونيكيشن. من يصير بور كوميونيكيشن هم قد يؤدي الى مشكله كبيره. المشكله عندهم هنا بال شركه الهازارد اناليسيز، اللي ما يعرف الهازارد اناليسيز اللي هو الهازارد او probability ريفيو، هذه نسويها دائما من تصير تغييرات او انت عندك سيستم معين نسوي له ريفيو دائما، خاصه تأتي في مرحله التصاميم، بس حتى بالتشغيل هي موجوده. من تريد تبدي سيستم او تضيف للسيستم تغييرات معينه كانابيب او مضخه او اي شيء، يعني اي تغيير لازم له هازارد. هو شنو الفكره؟ انه انت تقعدون تيم مشترك عندهم افكار معينه، يتناقشون بدراونجز او شنو التغييرات، بحيث تقدر الامكان تقللون المخاطر او تعرض الوحده او المعدات او الناس الى الخطر. فهاي النقطة مهمة، إضافة إلى النقطة الخامسة صارها مهمة تنطبق علينا بالعراق كثيرة، يعني انه السيفتي كلتشر. السيفتي كلتشر انه احنا كم فهمنا للسيفتي لابد ان يتغير، خاصه انتم الشباب يعني بعدكم فريش، ما متطبعين بطباع اللي هي قديمه مثلا، اللي المفروض احنا عموما ما نهتم بالسيفتي. بس الموضوع السيفتي كلتشر مهم، يعني انت من تشوف واحد خطا يؤدي فد عمل خطا مثلا داخل الوحده بدون سيفتي هيلمت مثلا، هذا انت توقفه، لا تسمح له. هي هاي الكلتشر شنو؟ انه اني وانت نتعاون بحيث ما نرضى بالخطا يعني. وصايره اكثر من موقف مثلا، حتى مستوى مثلا مدراء نقول له مثلا يا بالسيفتي انت ليش ما لابسه مثلا. فاقصد هاي الموضوع الكلتشر. او مثلا عندنا انا شايفه مثال دائما نذكره، انه العامل اذا بدلته تتوسخ ينظفها بالكيروسين، يعني هاي مأساة اذا تصير. فهاي موضوع الكلتشر جدا مهم. هاي الافكار لازم تنغرس ببالكم دائما، وتبنون عليها، وإضافة تسوون education للآخرين بهذا الموضوع، لأنه أنت تتعامل ويا معدات جدا مكلفة، وإضافة إلى تتعامل ويا وضع هو دائما خطر، عندك هيدروكربون، عندك غاز وسائل وضغط وحرارة، فبسهولة يصير الحادث. فهذا بس ردت يعني نشدد على هاي النقاط اللي ذكرت. Thanks Olga, you can carry on. Thank you. Unless you have questions or you want to discuss something, Shabab. Okay. Yes, you can proceed, Olga. Don't see any question.
Okay, thank you. So after this safety moment, let's gonna go with the index. In today's session, we have split this presentation into reboilers and condensers. So today we are gonna talk about reboilers, and next week in our second session of this training, we are gonna talk about condensers, and we will see some examples of reboilers and condensers in Carvala refinery. So in today's session, we are gonna talk about boiling phenomenon. We are gonna talk also about the introduction to reboilers, and we will see all different type of reboilers, and finally we will talk about how to select the correct reboiler to our design. Okay. I don't know how to minimize that. Okay, yeah, maybe now it's better, because I guess you were watching this the screening thing here, right?
Yeah, no
Now
problem.
it's better. Okay. So yeah, let's start with the boiling phenomenon. What is boiling? So boiling is a vaporization of a liquid, which occurs when a liquid is heated to its boiling point. So then the boiling point of a substance is the temperature at which the vapor pressure of a liquid is equal to the pressure surrounding the liquid, and the liquid changes into a vapor. When designing reboilers, we always check how boiling phenomenon is working along our heat exchanger. And we use to graphicate the variables we want to check. In this case, in this first graph, it is represented the temperature of the fluids along the tube length of a shell and tube heat exchanger in a reboiler. So on the shell side of the reboiler, we have located the MP steam. This MP steam is at 8 bar, and the inlet temperature is a little bit above of 175. Let me, yes. 175 degrees. So this MP steam is a little bit superheated. Okay. Okay. It's a little bit superheated. So what we see is when we enter into our reboiler, we lose some pressure, and then we achieve the saturated temperature a little bit above 170. And here we have already all this temperature, and it is condensing, while on the tube side, we have the processed liquid that we want to vaporize. The inlet is at 145, and the outlet at 140, above 46 degrees. In this second graph, it is represented the vapor fraction. It is represented the vapor fraction of the fluids along also the length from the length of the exchanger, the tube length. So we can see how the medium pressure steam is condensed along the shell and tube heat exchanger, and how the process liquid, it is vaporizing from 100% liquid, and the outlet, we achieve 5% of vaporization. So usually designing a reboiler with, for example, the HRI program, we used to graphicate these graphs to see if everything is working properly and everything is how it is. So again, what is boiling? The following types of boiling can occur in a reboiler. There are different types of boiling or heat transfer regions that can occur in a reboiler depending on the fluid properties like density and viscosity, also depending on the velocity of the fluid and also the design of heat exchanger. If it is designed vertical, horizontal, or with one type of baffles or another type. So these all these parameters have influence of the type of boiling we have in our reboiler. So then we can differentiate the following types of boiling. The first one, the nucleate boiling, where small bubbles of vapor form at discrete points. In this case, this is the most stable regime. Then we have the critical heat flux boiling and the film boiling. The first one, the boiling surface is heated above a certain critical temperature and a film of vapor forms on the surface. It appears when the heat flux increases to a maximum value. And the film boiling is a thin layer of vapor formed on the surface, which decreases the heat transfer. So it means that we have in our tube, we have like small bubbles that makes decrease the heat transfer because the transfer is not as good as, for example, here in the nucleate boiling, because we have this thin layer of vapor. And finally, we have the transition boiling. This is an intermediate between nucleate and film boiling and critical heat flux boiling. It is unstable form of boiling with elements of nucleate and film boiling. All these are different types of boiling areas. So when designing a reboiler for the first time, what we do is always try to be on the nucleate boiling part because it is the most stable region. So we will design our heat exchanger to have and to be on the nucleate boiling. And when I say design the heat exchanger to be in this part, it means that I will decrease, for example, the tube diameter to have more velocity and then to change the flow regime. Or I will add more tubes, or I will delete some tubes. So it means I will design my exchanger with the correct configuration to achieve the proper boiling regime. So after the boiling phenomenon definition, we will go to a quick introduction to reboilers. So what is a reboiler? A reboiler is a heat exchanger used to provide heat to the bottom of the distillation columns. The liquid is heated from the bottom of the distillation column, as you can see in the image here. So this liquid is taken from the bottom of the column and goes into the reboiler to generate vapors that are returned to the column for driving distillation separation. All vapors that drive the separation come from a reboiler of a classical distillation. The reboilers receive a stream of liquid from the bottom of the column and may completely or partially vaporize that stream. So as you can see here in this image, this is the typical configuration of a distillation column. We have the distillation column. The feed of the column is introduced in the reboiler. In this case, this is a kettle reboiler, where it vaporizes and returns to the column. On the tube side, we have the heating medium. This heating medium can be steam or it can be another medium, but usually it's steam. So we enter the steam in this case, a kettle reboiler, where it condenses and returns to the heater. So reboilers are classified into different forms according to the type of circulation and their orientation. We classify them in natural circulation and forced circulation. So we are gonna start with the natural circulation reboilers. In this sketch, we can see...
Okay, let's just check if they have a question on the definition.
Yes.
شباب واحد عنده سؤال أو استفسار على اللي انشرح من ناحية أنواع الريجن مال الريبويلنج والارينجمنت؟ تفضل أستاذ عبد الرضا.
السلام عليكم أستاذ. بالنسبة للريبويلر بمصفانة بس بالديستليشن لو أكو بغير مكان بغير وحدات؟
أكو هو عادة يعني أكيد ويا الأبراج بشكل عام يعني.
بس هي قصة كلها بس بالديستليشن يعني وين غير اكو غير مكان يا ريت
بالمصفى ما ادري يعني مو ببالي هسه بالضبط وين الاماكن مال الريبويلرات، بس انا احكي لك بشكل عام. هو يعني برج التقطير يكون موجود، اضافه مثلا ستريبر يجوز تحتاج لريبويلر، يعني تورات ثانيه مثلا تحتاج ريبويلنج. Olga, have you come across any of the reboilers in Karbala refinery in terms of is it just only CDU or there are a number of I'm assuming there are numbers of reboilers appear different units.
Yeah. At the end of next week we will see 2 examples of reboilers. One example of reboiler and one example of condenser. Yes, is a reboiler. Is a reboiler of a column. So we will see this example.
Okay.
Otherwise, if there is some reboiler that you want to see, just tell me and we can, because I have chosen one random reboiler. So if you have special interest to see a special reboiler, just tell me and we can see that one.
I'm pretty sure there are a number of reboilers.
Yes.
Oh, okay, no problem.
So but I have chosen one random reboiler with no special selection on the units.
Okay.
But if some of you has a special interest in seeing in detail some reboiler or at some unit, just tell me, and we can see that example, of course.
Okay, any more questions? Okay, no more questions. Yeah, you can carry on.
Okay, so we were saying that reboilers, depending on the circulation, we have the natural circulation or forced circulation. We start with the natural circulation. So in this sketch, we can see how the liquid flows from the bottom of the column into the reboiler, where it vaporizes and returns to the column. The main characteristics of the natural circulation reboilers are that the return piping to the column is sized for two-phase flow. The operation on thermodynamic principles rather than gravity. Also, thermosiphon operation is simple, but they are often difficult to design for a wide operating range. And finally, we need a proper elevation with the column and the exchanger, because since we said that the operation is on thermodynamic principles, we need to ensure a good hydrostatic pressure difference that allows the fluid circulation. So this elevation of the column with the reboiler is critical to have this liquid static head that allow us to circulate the fluid with the thermodynamic principles. So then we also have the forced circulation. As you can see in this picture, we see that the fluid is coming also from the bottom of the column, where there is a pump that pumps the fluid into the reboiler, where it vaporizes and returns to the column. So in this case, we have a pump who allow us to circulate the fluid between the column and the reboiler. The main characteristics of the forced circulation reboilers are that they are usually designed to operate liquid full. As you can see in the picture, this is full liquid. Flashing occurs as the liquid crosses the control valve, and valve should be located close to the column shell. They offer greater operational flexibility than thermosiphons, than natural circulation thermosiphons, and they have a smaller footprint than kettle reboilers. Kettle reboilers, we will talk about them later, but a kettle reboiler, as you can, if you remember, that was the first picture, the first sketch we saw in this presentation. And finally, with forced circulation, the elevation of the column is less critical because we have a pump and a control valve that allow us to circulate the fluid between the column and the reboiler. So here, since we are not, since the fluid is not circulating with the pressure static head, we do not need to locate and to be worried about the height of the column. So after defining what it is the natural circulation reboiler and forced circulation reboiler. We can see in this classification the different types of reboiler we can find in each group. In the natural circulation reboiler, in the natural circulation thermosiphon, we have the first group, the kettle reboiler. We also have the internal, also called bundle in column reboiler. And we also have the vertical and horizontal thermosiphon, split it into natural circulation or once through reboiler. And for the forced circulation, we have a vertical and horizontal circulation. So in the following slides, we are gonna see each one of these heat exchangers. We're gonna start with a group of the natural circulation. This is the most wide group with a lot of different reboilers. And finally, we will go for the forced circulation. So if you have any question until here.
شباب أحد عنده سؤال استفسار على الأنواع الريبويلرز؟
بني أستاذ.
تفضلي ست. نعم.
أستاذ بالنسبة للتصنيف مالتها جاي يقول circulation والorientation ما عرفتها هذه الثانية شنو؟
وين يعني بالناتشرال؟ صوتك شوي.
بصورة عامة أستاذ. هو مو يصنف إلى يعني
ناتشرال وفورست، يعني الفورست
لا عفوا اللي قبلها circulation والorientation ما أعرف شنو هاي. أصلاً ما أعرف معناها.
اورنتيشن احمد اورنتيشن.
الاورينتيشن يعني معناها الارينجمنت، يعني
ترتيبها الشكل
مالتها. يعني انت
ترتيب الشكل مالتها شلون هسه هذه؟
بالضبط، يعني شلون انت ترتبيها. مثلا هسه خلينا نعطيك مثال ثاني، مثلا تقولين الغرفه الاورينتيشن مالتها باتجاه الشمال او اتجاه الشمس. يعني اقصد ترتيب الغرفه او ترتيب المعده الاورينتيشن مالتها.
يعني هسه مثلا هذه افقي وعمودي لو لا؟
اي هاي يعتبر الاورينتيشن مالتها مثلا فيرتيكال او الاورينتيشن مالتها هوريزونتال، يعني ترتيب المعده شلون شكل.
بلي هذا. شكرا. فهمتها.
اوكي شباب، احد عنده سؤال او استفسار؟ Okay, I think Olga, you can carry on. Yeah.
Okay, thank you. So, as we said, we are gonna talk about each of these exchangers. And we are gonna start with the first one, the kettle reboiler. Kettle reboilers, also called a submerged bundle reboiler, are commonly applied when a wide range of process operations, high turn capability, large heat exchange surface, or high vapor quality is required. Installations include bottom reboilers, side reboilers, or vaporizers, and they are often used as vaporizers as a separate vapor liquid disengagement vessel is not needed because the kettle has an area above the tube bundle which works as a vessel and separates the liquid and vapor. Finally, they are suitable for vacuum operation and for high rates of vaporization up to 100% of the feed. So let's gonna see a bit this sketch. We have the bottom of the column which enters into our kettle. The kettle, it enters into the shell side where it fills of liquid up to the weir plate. Here we have a plate. This is filling with liquid, and here it starts to vaporize. We have this space here called disengagement space that we can say that this, because we can say that this is like having a vessel after the reboiler to have the difference between vapor and liquid, to separate the vapor and liquid. So this is why it was written here. This is why they are used as vaporizers, because there is no need of having a vessel, since we have this disengagement space above the tube bundle. So then here we have this vapor liquid separation, and then we ensure having 100% vapor into our column inlet. So kettle reboilers consist of a tube bundle, and we see here supported by plates. The structure of tubes can be either straight tubes or U-tubes. As you can see in this sketch, we have U-tubes. The tube bundle is placed inside a large, specifically designed horizontal shell known as the Mackay shell, as this one. This is a K-thema type. And the most common thema types are for fixed tube sheet, AKM, BKM, or for removable bundle, AKS, AKT, and VEU. In this case, in this sketch, we are having an AKU. So usually, kettle type is provided with a weir inside the shell to control the level of the liquid. This weir is this plate, this liquid level plate, where the vertical length of the weir dictates what quantity of liquid will be retained in the shell. So we have the shell side inlet flowing into our shell side. This is filling up with liquid until the top of this liquid level plate. And since this is full of liquid, then this retains the liquid in this part, and an excess of this liquid will be dropped into this area where we will control the height of our liquid. It is important, this liquid plate, this weir plate, because the tube bundle must compulsorily be immersed inside this quantity of liquid at all times during the runtime of the process. It means all the tubes must be covered by liquid. How does it work? We already have talked a little bit, but in this sketch, you can see more or less how it works, the fluid. The liquid to be vaporized flows through the shell. We have here the liquid inlet, flows through the shell due to the effect of gravity maintaining an adequate head with the column. The processed liquid covers the tube bundle entirely, and this liquid, commonly called bottom, is commonly called bottoms in distillation process. For the heating fluid, we have the steam, usually steam. Sometimes we have oil, depends of the heating fluid we have. The steam flows through the tubes. Pass partitions are provided to get highly effective heat transfer relative to single pass. It means here we have 2 tube passes, so then we increase velocity and we increase the heat transfer, the heat transfer, instead of having 1 pass. And finally, above the tube bundle, there is the vapor disengagement area. You can see in this part, where the liquid is separated from vapor, and thanks to that, it can reach rates of vaporization up to 100%. So the main advantages of having a kettle type reboiler is that they are very stable in operation because kettle type is relatively insensitive to system hydraulic changes. As a result, it is reliable even at very low at vacuum or high near critical pressures. With kettle type reboiler, we have a good control at large operating load variations or tear down ratios. And finally, the separation efficiency of the boiler approaches to 1 theoretical stage in the column. And the main drawbacks of kettle type reboiler are that the oversized Temake shell makes exchanger more expensive than other reboilers because, as you can see, the K shell is very big, so that's a lot of material and it's more expensive than other reboilers. They have a low circulation rate that make kettles very susceptible to fouling. Since the circulation rates are low, the velocities are also low, so then we have sometimes depositions, so they are susceptible to fouling. And finally, we need a big plot area to place a kettle, since we say that K shell are very big, so we need a large plot area. So this is all for kettle reboilers. If you have any question, please let me know.
Yes, Olga, could I ask something?
Yes.
If we could back for page number 14. No, before that.
15? This
14. 14, no. Yes, this one.
Yes.
Maybe we must correct the place of the feed come from tower to the kettle, reboiler. It's not maybe from bottom, exactly. It's from the place we name it the chimney tray.
Well, yes, it depends of the type of the column. Yes, this is just
the place up to the back of the vapor.
Necessarily that every distillation
To let the pipes, all the steam pipes immersed with covered with the liquid.
No, but just to let you know that not every single distillation column has got a chimney tray in the bottom. Not necessarily.
Not in the bottom, Ahmed. It's the above the الشوتات مال البخار فوقها.
لا بس
والبخار يرجع. بس شغلة ثانية أبو يوسف بس خليني أكمل لك. The material what we separated it's after this plate of the accumulation. It must bag, not go out directly to as a product. It's maybe back to the tower, and then it's accumulate inside the tower bottom, and then go to the what is the place it must go.
First of all, this is just a simple.
Just to need to correct the paragraph or the diagram.
This is just to simplify the idea of the routing.
Yeah.
So it's not. This is just a simplified diagram.
Maybe somebody not know. He's not know the exactly what is going. Maybe this idea will stay in his mind. So maybe it's not correct for from this time.
Well,
to
it depends.
Let them.
Yes, but it depends of the distillation column. There are the bottom of the distillation columns. We have a white
White kind. Yes, I know white kind, different kinds. But
so
the place. I'm asking about the place.
About the bottom of where we take.
Yeah.
But
yes,
there are columns that we take the feed from the bottom of the column.
Not exactly from this bottom, Olga. It's that the place under the vapor return. Also the product from kettle reboiler. It's back to the also back again to the tower, and then it's accumulate, because if we use just this small level from kettle as a product, maybe it's be batch product, not continuous product. It's very small every time.
But here
just maybe just correct the diagram if you accept.
No, well, actually, this is a diagram. This is a typical diagram to explain how a kettle is working.
Yes.
Because actually, this is not focused
not
on the columns. It is focused on the kettle, actually.
Yes, the practical it's maybe different, some different in the practical.
Just to enlighten this discussion.
Yeah.
This diagram, how the reboiler gets the flow and how you emerge the U-tube arrangement under the liquid. This is, we're talking about the idea of the reboiling. But what you have seen, say for example, you worked in the north or in Dora, you've seen different arrangement for reboiler. But here we talk about general. So and what you've seen, like say for example in Dora does not generalize all the arrangements in the world.
Yes. Okay.
But this is just a principle. Say like for example, you mentioned chimney tray. Not every single distillation column in the bottom there is chimney. No. So this is just general arrangement. But you are comparing it to, for example, in Dora refinery, it's different arrangement.
Yes.
True. But
just we need to focus on one idea for the kettle. We need every time we need to immerse all pipes of steam with liquid.
Yeah.
So every time must the level in the tower up to the place up to the pipes of kettle or of the steam pipes. So this is my idea. Just to focus on this one. This is my idea. Everything is
principles. Yeah, but you cannot quote this and you say, "Oh no, that's not correct because in a different reboiler arrangement is different." This is not to apply the exact arrangement.
We will see it. We will see it in the practical in the units of our refinery, and after that we saw.
Yeah, the idea of this slide is just to know that the kettle type arrangement.
How it's recycled? Yes. Okay, recycle the liquid. Okay.
Why the liquid in the column is the same level as in the reboiler. So this is the messages you have to take.
Yes, this one. This one.
And then beyond the liquid level, on the top of the liquid level is only you have vapor space where you allow for a liquid vapor disengagement, and then that's why you get 100% vapor. So these are the information you need to get from this slide.
From this slide, yes. Okay, thank you. Thank you very much. Thank you, Olga. Thank you.
Thank you. Thank you for your comments also.
Yeah, you can.
Okay, thank you very much.
Okay. Okay, so now we have seen the kettle. Now we go to the vertical thermosiphon recirculation. reboiler. So the first point is that vertical thermosiphon reboiler is a vertically mounted single pass shell and tube heat exchanger with the boiling fluid located on the tube side. Single pass, which means we have only one tube pass per tube side. The liquid passes from the bottom of the column into the reboiler, with the evaporation taking place inside the tubes. The heating fluid, typically condensing steam, is placed on the shell side. The two-phase mixture is discharged back into the column, where the liquid settles back to the liquid pool and the vapor passes up the column as shown. The vertical thermosiphon reboiler is less susceptible to fouling problems than kettle, and in general, it has a higher heat transfer coefficient than kettle reboiler. And finally, additional height is required in order to place the reboiler. So remember that, so since we have to ensure a good hydrostatic pressure difference or a liquid static head that allows the flow to circulate between the column and the reboiler, sometimes we need to elevate the column a few meters to place our reboiler below the distillation column to ensure this hydrostatic pressure and to ensure this circulation flow. Yeah. So the main advantages of vertical thermosiphon recirculating is that the exchanger is cheap. When I mean is cheap, is the price is lower than a kettle reboiler, since the shell is not K, so is smaller than kettle reboiler. Since this is since it is small, we also need low plot area requirements. We can achieve high circulation ratio, so this leads to have high heat transfer coefficients and low fouling. The single pass tube side arrangement facilitates cleaning, and it can be performed without removing the exchanger. And finally, the process fluid that we are vaporizing is on the tube side, which is an advantage for corrosive fluids. And the main drawbacks of vertical thermosiphon are that evaporation rate is maximum 35%. Remember that for kettle reboilers, we can achieve 100% of vapor at the inlet of the column. Here with the thermosiphon, we can ensure only 35% maximum. The column usually has to be raised to above the boiler, requiring an increased skirt or additional steel work. Also, the performance tends to be poor near critical conditions, where the liquid and vapor have similar densities, thus giving little force of recirculation. the turn down is limited. It can be unstable in operation with circulation and vapor generation varying. So kettle reboiler, vertical thermosiphon reboilers do not like having variations in their operation actually. So they are stable where there are no changes in flow rate, for example, but when some differences in flow rate occur, they are not likely to be stable. Remember that we are working on with the pressure static head, so we need to have unstable recirculation to have a good liquid flow circulation. Also, being a single pass design, it is difficult to allow for differential expansion other than by shell bellows. It means that when high temperature difference occurs in our heat exchanger, in our vertical thermosiphon reboiler, since we have a single pass, tube single pass, we are likely to have some expansion problems, so we will need to add expansion joints or bellows. And finally, the boiler does not contribute a full theoretical stage to the separation. So we have finished the vertical thermosiphon recirculating reboiler. See if you have any question.
Yeah, thanks, Olga. Guys, do you have any question? عندكم سؤال على الكتل تايب على الفيرتيكال ثيرموسايفون والناتشورال سيركوليشن؟ نعم استاذ عبد الرزاق.
حياك الله عزيزي استاذ احمد، شكرا جزيلا. العفو استاذ، بس بالنسبه للسايفون او الثيرموسايفون، ليش يعني هالتسميه هذا؟ يعني حسب علمي كلمه السايفون دائما تستخدم بال يعني من اكو فد اكويبمنت معينه يصعد بها ليفل الليكويد ويصير يعني ميكانيكالي اوتو، يفرغ ويرجع يترس، يفرغ ويرجع يترس.
خلي اخذ اذا عندك سؤال ثاني مو مشكله، بس خلي اسال لك اولغا حتى تجاوب. Olga, the question is why we call it thermosiphon. You know, the research vertical thermosiphon, horizontal thermosiphon. So the term thermosiphon, what's the definition of the thermosiphon?
Because it is thermosiphon because the flow circulation is what it is called thermosiphon flow. It means that they are flowing with a different of pressure static head. So the thermosiphon concept is attached to the recirculation.
Sorry, if you don't mind, if you go back to the diagram and
yes,
so at least they can visualize it. Thanks.
I think here it's quite good. Since our reboiler, the flow circulation, it's working called, as we say, thermosiphon. Thermosiphon, it means that the flow is flowing according to the process, to the pressure static head. So thermosiphon means that the fluid is flowing according to the density difference and the pressure difference between the column and the reboiler. So it is what we call the thermosiphon concept.
Yeah. استاذ ما اعرف اذا واضح الجواب، لو تريد تعيده.
ممنونين، لا شكرا جزيلا. يعني فهمت يعني القصد مالتها، بس انا بس عندي كان الكونفيوجن اللي هي كلمه سايفون، يعني حسب شيء علمي انه هي دائما تستخدم بهاي الانظمه اللي هي بها ليفل يصعد واوتوماتيكلي يعني.
هو استاذ رزاق نفس الفكره استاذ.
فيعني انا قصدي
يعني هو اكو باج مال ليكويد جاي يجي للريبويلر نتيجه التبخير راح يتحول من السائل للفيبر، رجع اجت باج ثاني وراح اجى باج ثاني وراح، نفس سالفه السايفون بالضبط.
يعني خلينا نسميها هي طيباتشات نظام يعني
باجات ليكويد بالضبط، يتحول كل الليكويد الباج الى فيبر، راح اجى اذا باج ثاني بدال الليكويد بسبب فرق الكثافه والدفع الضغط مال الارتفاع،
يعني شلون اكو
تحول فصار سيركوليشن.
يعني اكو شلون الفالف الاكويبمنت معينه مسؤوله عن
مو فالف ماكو، لا 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 على كيفك، لا بسبب فرق الكثافه والارتفاع. البرج بارتفاع ومادته بارده، تنزل وين؟ للريبويلر. الريبويلر البايبات بها بخار راح تسخن الماده تتحول الى فيبر، الفيبر اخف يصعد لي فوق يرجع للبرج، راح تصير هاي الحركه الدورانيه بسبب
يعني مدى تخيلها انه تصير باتش، يعني راح تصير كونتينيوس
بالضبط كونتينيوس، بس باتشات بالليكويد، يعني الليكويد يجي بمكان الليكويد الثاني والليكويد يجي بمكان الليكويد الثالث والرابع، فتصير سيركوليشن حركه تدوير،
يعني ما يقطع
ما يقطع. هي هاي نفس السايفون تقريبا، يدفع ويرجع غيره، يدفع ويرجع غيره.
اوكي ممنون، شكرا جزيلا.
هو يعني هم باختصار يعني معناها انه انت ما تحتاج تول او كيت مثلا ميكانيكال بامب حتى تسوي هاي السيركوليشن، هي حتى تصير ناتشرال، فهي هاي الفينومينا اسمها ثيرموسايفون.
استاذ يعني قصده عذرا يعني عن المداخله استاذ، مقصود هنا بدون فورس درافت؟
لا ماكو اي فورس ماكو بالضبط.
احنا بدنا نحكي عن ناتشرال هسه، ناتشرال سيركوليشن تايب
بالضبط.
بعدين يجيكم الفورس هسه شوي.
بالضبط. هو فقط انه انا كان يعني استفسار كلمه سايفون، يعني سابقا مر علي انه تصير يعني يقطع فد ليكويد هذا فاس، فيبدو انه هي كونتينيوس ماكو قطع
كونتينيوس ماكو قطع بالموضوع.
شكرا جزيلا.
بس فقط بسبب الباجات تتغير قطع السايفون.
عندك سؤال ثاني كان استاذ عبد الرزاق؟
ممنون. لا شكرا جزيلا حبيبي الاستاذ.
منو عنده سؤال او استفسار ثاني؟
استاذ
نعم ست هلا
الداتا شو يعني لو ترجع للنقاط
يا سلايد
هي نفس هذا
يعني نكست سلايد في 19. لا هي
المميزات اللي كانت الفايبريشن اعلى من 35 وكذا، فعندي نقاط ذي اريد استفسر عنهم.
Sorry Olga, if you go to slide 19 if possible. The drawbacks and the advantages are there. هاي ست ملاك هاي. بعد. Next, so I think the drawbacks she's asking about. Yeah.
بلي هذه. Point 2, the column usually has to be raised to be above the reboiler.
بلي.
هذا الكولوم أي كولوم يعني المقصود بالكولوم منو هنا؟ ممكن الديستيليشن
أي كولوم، يعني المصدر السائل اللي يجي التردين تسوي له ريبويلينج، هذا المصدر اللي يجي السائل يكون أعلى. أي بالضبط، حتى أنت شنو يو ميك شور إنه الليكويد يروح. ليش؟ لأنه إحنا ما نستعمل مضخة، فلا مثل انت عندك خزان بالبيت تردين تنقليه مثلا الكونتينر صغيره مثلا حاويه صغيره، فلازم مرتفعه حتى انه تتاكدين السائل ينتقل، لانه اذا بقيتين نفس الليفل السائل ما راح يتحرك لانه ماكو مثل مضخه تتحولها.
بلي then point 2 3
the performance
tend to be poor near critical condition where the liquid and vapor have similar همين يعني نفس هذا.
اي هو يعني المشكله مالته وين؟ اذا انت مثلا يعني مثل البرج التقطير مثلا اذا تريدين تعزلين مثلا الايزوبيوتين او مثلا البيوتين من البروبين، فلاني كلش متقاربات الدنسيتي مالتها، فعمليه الريبويلينج تصير شويه صعبه. ليش؟ لانه الدنسيتي متقاربه، هذا معنى. فلذلك يكون هذا النوع من الريبويلر مو احسن مثلا من الكتر مثلا. خليه هي تجاوب كذا، يعني هي بعد نيم حضره. Sorry, the question here about what's the meaning of performance test near critical conditions where the liquid and vapor have similar density. So if you just give some information about this point, thanks.
Yes, this is actually according also to the first question you asked regarding the thermosiphon meaning. So since the thermosiphon meaning is what thermosiphon is, the effect of the thermosiphon is the phenomenon of having this fluid circulation having by the difference of the densities. When we have a hot fluid, the density, we have less density, so then the fluid goes up, and on the contrary, the fluid goes down. So this is how the thermosiphon is flowing. So when we are working with a fluid where near the critical conditions, this movement, this thermosiphon effect is not very well done. So then the performance is poor. It means that the circulation is not as good as if we are working far from the critical conditions. So since the circulation is not as good, our vaporation ratio is not good also. So because the thermosiphon effect is not as well done as we are working far from the critical conditions.
How I know near a critical condition?
Because you need to know the nature of your process fluid. If you are working on the critical conditions or not.
Yeah, so do you mean by critical condition like you near, for example, the critical pressure, or you mean critical condition in terms of the densities are very marginal different?
Yes,
I get it.
The second one, near where the densities are very similar. Yes.
Okay.
I get it. Thank you.
Okay.
You're welcome.
يعني اللي هو القصد انه اذا مثل الدنسيتي الفلويد الدنسيتي مالته مثلا 980 والفلويد الدنسيتي مالته 970 فهنا لانها اكو متقاربه. لذلك مثلا هسه ايش عندنا الدي ايزوهكسنايزر اتصور واحد من اعلى الابراج موجوده عندنا بالمصفى. ليش؟ لانه الفصل بين مقاطع متقاربه بالموليكولار ويت بالمواصفات، فش يحتاج لنا نمبر اوف تريس كلش عاليه، فهذا نفس الشيء يظهر لنا بالريبويلر. لذلك لازم النوع يكون يتقبل القرب بمواصفه الدنس
بالكثافات.
هذا طبعا يتعلق بالتصاميم يعني.
طيب أستاذ، بعد هم عندي سؤال. إذا يعني قلت إذا يعني بعدين من تنتهي المحاضرة أو هسه إذا يعني أنه
نعم تفضلي سمعت.
what type يعني من يعني ما هي نوعيات الريبويلر اللي يمتلك single phase liquid واللي يمتلك يعني two phase liquid؟
خلي بالاخير let's leave this
اي بلي هو قلت حاب يعني
يكون all the other types of reboilers then you can decide.
بلي thank you grateful to you.
استاذ احمد
تفضل استاذ. هلا استاذ مرتضى.
السلام عليكم اول مره. العفو استاذ احمد، بس بالنسبه لموضوع البرفورمانس 10 تو بور نير كريتيكال، هو يعني مو المقصود انه اني هذا النوع من الريبويلر يصير ظروف العمل قريبه من الكريتيكال بوزيشن مالت الفيز دايجرام للليكويد مالتي، فبالتالي راح يصير الليكويد والفيبر ماكو فصل بيناتهم.
انا هم سالتها هذا، هل تقصد
يعني انا راح اشتغل بظروف اللي هي السوبر كريتيكال فلويد اللي
لا
سوائل الحرجه؟
لا سالتها هذا السؤال اذا يعني سمعتني، قالت لا مو هذا القصد. القصد انه انت مش تسوي، انت غردت انت بتغلي سائل، فش تسوي؟ تو فيس او تسوي فيبر، صح لو لا؟ بس اذا هذا السائل اللي تسوي له ريبويلنج هو هم مالتي كومبوننت، صح؟ يعني اقل شيء بيه اثنين كومبوننتس، مثلا افرض بيوتين وايزوبيوتين مثلا، فذني راح تكون المتقاربات، لذلك هي كاتبه كريتيكال كونديشن. بس كريتيكال
بس بعدين هو موضح انه where the liquid and vapor have the similar density، انه شو وقت يتساوون بالدنسيتي، يعني من يصير عندك كريتيكال بالمنطقه الحرجه راح يكون الفصل.
لا مو كريتيكال، ما منطب هذا الكريتيكال كلش عالي، يعني احنا ما عندنا تشغيل انت تشغل الكريتيكال، ماكو ما عندنا تشغل فلويد بالكريتيكال بريشر وكريتيكال تمبرتشر.
هو هنا القصد انه هذا الناتشرال سيركوليشن ممكن يوصل لهذه الحاله.
لا
فهمتها يعني.
انا وياك
لا ممكن تند يميل هو جاي يميل لهاي قريب يصير نير كريتيكال كونديشن.
استاذ تسمعني؟
وياك استاذ الصوت راح وجه.
اي القصد شنو انه الكريتيكال I think all guys is just this lead to confusion when you say critical. Some people, you know, they directly goes to pressure, critical pressure and critical temperature of a fluid.
Okay.
Yeah.
Well, actually, in the vicinity of critical point, the physical properties of liquid and vapor change dramatically. So both phases become more similar, and then it difficults the thermosiphon effect.
Yeah. So give example of a fluid, for example. Which one is it close?
Sometimes, for example,
I said, for example, isobutane and butane. If you want to separate those two components in a column and you have a reboiler, then this you know drawback it appears because isobutane and butane, they are very close to each other in terms of molecular weights, in terms of physical properties, and that's when you're gonna have the poor reboiling, because they are very similar in density and the physical properties and conditions.
Yes, that's a very good example.
Yes, it's nothing to do with the critical pressure and the critical temperature. That's the bottom line. Yeah, people, they think about critical pressure and critical temperature, but it's not.
No, it's regarding the critical condition, the critical properties, critical in terms of temperature.
Okay.
Temperature and then the effect on density.
واضح استاذ احمد، شكرا.
Thanks, Olga. Any more questions, شباب؟
استاذ احمد اذا ما عندك مانع ناخذ الاستراحه؟
اي
ناخذ الصلاه.
بس ملاحظه،
ثلث.
بس ملاحظه واحده قبل ما ناخذ استراحه. استاذ عدي، يعني انت هاي هم يمك الموضوع، واستاذ احمد لاحظت فد شغله انه احنا بدينا 50 اول ما تبدا المحاضره، بس خلال 45 دقيقه وصلنا 80 و90. اكو ناس تطب ورا 40 دقيقه، ورا 35 دقيقه من المحاضره، فيعني ما اعرف انا، يعني المشكله مو مثل واحد اثنين اوكي، بس مو 40 يعني.
كل ما دا اسجل حضور شو دا يزيد لو دا ينقص يعني دخل.
استاذ احمد عذرا احنا بوقت متاخر جماعه الميكانيك صار عندهم علم.
لا دا احكي 4 اشهر استاذ ماجد، مو على اليوم.
لا انا عاد احكي عبالي على هاليوم.
مو على اليوم.
اليوم احنا لانه ظرف طارئ صار في وقت متاخر سمعنا بالمحاضره، فجماعتنا دخولهم صار ربما شوي متاخرين.
مو يمك استاذ بهجت، هاي احنا من الشهر السابع الشهر ال 11 هسه احنا لازلنا يعني
عذرا شكرا.
فشباب رجاء الالتزام بوقت المحاضره، لانه يعني نص الوقت مالته بس ادخل ناس يعني.
استاذ احمد اذا تسمح لي بس مداخله بسيطه. احنا دا يصير عاده هسه مثلا انا دخلت ذاك الاسبوع لكن النت ما اسعفني، يعني انه كملت جزء، يعني قصدي انه هواي دا يصير ويا الزملاء البقيه يحضر جزء، النت ما ساعده، دمرت المحاضره ما افتهم من عنده شيء.
انا دا احكي عن شيء دا اجيبه هسه بالطاري، لانه هو شيء مو اليوم ولا البارحه ولا انت ولا 2 3، نحكي ظاهره من احنا صار لنا 4 اشهر ننطي من جولاي بدينا لهسه، فالموضوع هو نفسه موجود، فيعني هو واضح الموضوع. موعد المحاضره ب8، انا انطيت 5 دقائق بس انا نظل ندخل ناس لمده 50 دقيقه، فمو صحيح يعني. هاي مو يعني مو الشخص موجه الشخص، ما احكي عن شخص واحد او اثنين او ثلاثه، بدنا نحكي 40 يعني. فهي من استاذ عدي واستاذ احمد. اوكي شباب
عاد والله ابو يوسف، يعني انت حدد موعد معين للدخول، بعدها لا تسمح لاحد يطب، انت يمك الموضوع.
ما اريد يعني ما اسمح.
يعني احنا يدرون الولد ساعه ب 11 خلي مجال 10 دقائق ما يخالف.
لا صعب ما اسمح، بس
مو ساعه، هسه انا
يعني
سجلت حضور يعني
50
هسه
دقيقه.
انا صاير دايخ بالحضور، ياهم ادخلهم وين يعني، يا الاسماء جاي اسجلها.
الفرق بالوقت يعني ما يحضر واحد
حتى ما جاي يتواصل ويا المحاضره والهاي، يعني من وراء هاي الموضوع الحضور.
5 دقائق اوكي، تتاخر 10 دقائق اوكي، بس مو 40 دقيقه او 50.
اي انت لا تدخله بعد، يعني اللي يجي ورا هذا الموعد لا يدخل، ما لازم.
يعني اي ما ادري والله، يعني شباب شويه اريدكم يعني ويانا تساعدون، لانه هاي فرصه لكم ومواضيع حلوه، مواضيع مهمه يعني، وماكو دوام. يعني انتم مثلا ماكو دوام اقصد رسمي، هسه الصور قليل بالعراق بسبب ظروف كورونا، فيعني شويه على كيفكم ويانا، واللي اجل مصلحتكم، ولا ما عندنا شيء احنا، عسى لو يحضر واحد اتس اوكي.
هسه البنيه باقي يا احمد، خليه تروح وباستراحه.
Okay, we can take a break half an hour if you want.
Okay.
Yeah, thanks.
Okay,
Until 1 p.m.
Until in your time.
Okay.
Okay.
In our time 1 p.m. Yes. In your time, I don't know what.
11. Okay.
11. Okay, that's okay.
Okay.
Okay, thank you.
Thank you.
شباب يعني شوي.
يا شباب. ماشي ابو يوسف.
اوكي شكرا جزيلا شباب، يلا نص ساعه ان شاء الله او بالوحده عندكم الصور نرجع. Okay, welcome back guys. Olga, I think we can resume now the presentation. Thanks.
Okay, thank you. So in this first time we have talked kettle reboilers and vertical. We have talked about natural circulation reboilers, where we have placed the kettle reboilers, and the vertical thermosiphon recirculating reboiler. So now we are gonna talk about the once-through reboiler. Is another type of vertical thermosiphon reboiler, the one you see in this sketch. This reboiler is a reboiler where the liquid comes from the column, is heated only once, and this is why this is called once-through vertical thermosiphon reboiler. So, as you can see in the sketch, the column outlet liquid comes from the side where it enters in the reboiler, and the return to the column is also on the side where the vapor goes up and the liquid goes to the bottoms. It is not recirculating because the liquid only is heated once. So the characteristics are that all the liquid from the bottom tray flows to the reboiler. Also, none of the liquid from the bottom of the tower flows to the reboiler. And all the bottom's product that comes from the reboiler goes to the bottom of the column. So all the liquid comes from the reboiler goes to the bottom of the column. When the once-through thermosiphon reboiler is working correctly, the reboiler outlet temperature and the tower bottom temperature are identical. And here if we take a look on the sketch, I put the sketch of the thermosiphon we just saw before the break, the vertical thermosiphon recirculating, just to notice the difference according to the once-through. Since here we have a recirculating thermosiphon where the bottoms comes to the reboiler and it vaporizes, and we have here circulation. Here, the main difference with the once-through reboiler is that the side stream coming from the plate, from the column plate, is only heated once, and the liquid bottoms goes to the as a product. And in this slide, I just wanted to do a summary of all the exchangers we have seen up to now to see the main advantages and disadvantages of what we have explained. So for the kettle type, the main advantages are that they are very easy of maintenance, since for cleaning, usually we can pull out the bundle and we can clean them. Also, we have the vapor disengaging area. So these avoid us to have a vessel, and then we have 100%, we can ensure having a vaporization rate of 100% at the column inlet. Also, the low skirt height for the column, since we usually do not have to put the column very high regarding to the kettle. Is easy to control, and there is no limit of vapor load. And as disadvantages, we have the extra piping and space, since it is a very big exchanger, which has also high cost. And it falls with dirty fluids, since the velocities are not as high as for the vertical thermosiphons. The second reboiler we have seen in this presentation, the vertical natural recirculation. As an advantage, we have the simple piping and compact. So hence, the cost is lower than a kettle. The main disadvantages are that it falls easier than one screw reboiler, since we are recirculating our bottom column fluid. They are difficult to maintain because even we can clean the tubes, we cannot take out our tube bundle. And also the main disadvantage is the high skirt height, because as we said, we need to have enough height to allow our fluid to recirculate. And the last one, the vertical one screw type. The main advantage is that they are not easily fooled, and the cost is lower than a kettle. The main disadvantage is the high skirt height and the no control of circulation, since all the liquid from the bottom tray in this place flows to the reboiler. Okay, so up to now we have finished with the natural circulation with vertical thermosiphons and the kettle. So we will pass to the natural circulation horizontal thermosiphon, but first, if you have any question, please just let me know. Okay, so I guess there are no questions.
Guys, any questions?
I don't know if something written in the chat.
No, I think there's no question.
Okay. So let's go to the horizontal thermosiphon. Remember, we are still on the natural circulation. So now we are gonna explain the horizontal thermosiphon. Here, this is the main, I'm sketch explaining a little bit the flowing system. So the horizontal thermosiphon reboiler is a horizontally mounted shell and tube exchanger with the boiling fluid on the shell side and the heating fluid inside the tubes. Remember, for the vertical thermosiphon, the fluid that we wanted to boil, it means the process fluid, was located inside the tubes. For the horizontal thermosiphon, the boiling fluid is located on the shell side, and the heating fluid, as steam, for example, it is located inside the tubes. The thema type are X, G, or H shells used for this purpose. Selecting one or another, it will depend on how many nozzles we have at the outlet and also the pressure drop distribution inside the shell. But these three thema types are the most common one for the horizontal thermosiphon reboiler. So how it works, the liquid from the column passes in cross flow over a tube bundle, and the liquid vapor mixture is returned to the column. The design has the advantage of preserving the natural circulation concept while allowing a lower headroom than the vertical thermosiphon type. When it means a lower headroom, it means that the height between the column and the reboiler is lower than the height with vertical thermosiphon. So then the head, hydrostatic head, it will be easier to have it, and usually there is, usually with horizontal thermosiphons, the column is, there is no need to, usually we have to put it above the exchanger, but less than with vertical thermosiphons. However, there are more uncertainties about fouling and about the prediction of the cross-flow heat transfer rates. Regarding fouling, in vertical thermosiphons, since we have the boiling fluid inside the tubes, we achieve higher velocities, then it is better to avoid fouling. In horizontal thermosiphons, since we have the boiling fluid on the shell side, the velocity is lower. So then sometimes we have depositions of the fluid and we have more fouling. So the main advantages of the horizontal thermosiphon are that the exchanger is relatively cheap. It means it's less costly than kettle reboiler because the shell is smaller, so we do not have to invest in material as for the kettle. Multipass arrangement for the heating fluid can be used, so thermal expansion can be accommodated. Also, removable bundles are possible for cleaning. High circulation can be achieved, leading to high transfer coefficients and low fouling. This is compared to the kettle type. And finally, the elevation of the column is less than for a vertical thermosiphon reboiler. And as drawbacks, we have that larger plot area is required than for a vertical unit, especially if the bundle is removable, because we need to keep some area free to take out the bundle. Also, the process fluid is on the shell side, creating potential problems with fouling or corrosive fluids. So as we talked in the first presentation we did with regarding heat exchangers, for fouling or corrosive fluids, it is better to place them inside the tubes than the shell side. So since with horizontal thermosiphon, the boiling fluid is located on the shell side, we have to keep in mind that if we have a fouling or corrosive fluids, this can lead a problem in our design, and we prefer to have these fluids inside the tubes, so then with a vertical thermosiphon. And finally, the boiler does not contribute a full theoretical state to the separation as the same as for the vertical thermosiphon. Okay, and finally, the last type of reboiler of the natural circulation part, we have the internal reboiler, also called bundle in column reboiler. Internal reboilers are also known as stamped-in reboilers or stamped-in bundles. They are another special application of the horizontal reboiler design. The internal reboiler is usually used where the process can be on the shell side and the reboiler surface area is small enough to fit into the distillation column sump. It means that our process fluid, the boiling fluid, will be on the shell side. As you can see, this is not shell material. It's like we have no shell. The shell is the column. So we insert the tube bundle into the column, where on the shell side is the process fluid, the boiling fluid. And inside the tubes, we have the heating medium as steam, as we said, and we have U-tubes. So boiling takes place in the pool of liquid at the bottom of the tower, and the heating fluid goes inside the bundle of tubes. Also, we have to keep in mind that since the boiling liquid forms foam, which may vary in density, controlling the bottom level can be difficult. For that reason, this exchanger is not very common for vacuum services. The main applications for internal reboilers are the following. For batch distillation, where the tube bundle can easily be fitted into the batch drum and periodic cleaning can be easily done. Also for very low heat duty clean services, where column diameter is large due to other considerations, and where the reboiler tube bundle is small. It means that we need low duties. It is better to have low duties to place an internal reboiler inside the column, because the problem of designing this type of heat exchangers are that we are limited. We have the area very limited, so then we have limited the tube length according to the diameter of our column. And usually internal reboilers are used when our duty is low. So, as we said, these reboilers have the limitation imposed by the size of the distillation column. The main advantages of internal type reboiler are that no thermal expansion issues, since tubes configuration are U tubes, so then we can manage this thermal expansion in the U area. Very low cost, since there is no shell construction. And the separation efficiency of the boiler approaches one theoretical stage. And as drawbacks of the internal type reboiler, you have that the heat transfer surface limitations. It is usually only used with large diameter columns. Also, not recommended for vacuum services. Yeah, and that's all the drawbacks for internal type reboiler. The next slide we will talk about forced reboilers. So we have finished with the natural circulation reboilers. If you have any question of this first block, please tell me.
شباب أحد عنده سؤال أو استفسار على الناتشرال سيركوليشن كله لحد
هذا أحمد إذا ممكن
تفضل.
بس توضيح هاي العبارة not recommended for vacuum surface.
إيه.
يعني شنو السبب وشنو اللي يصير مثلا بهاي الحالة؟
Okay, so Olga, what happens if the vacuum occurs in a column? That why we cannot use this type of reboiler?
Mm-hmm. Yes. Well, actually, vacuum columns, vacuum reboilers, all vacuum services are, we have to control very well all pressure at each part. So with this type of reboilers, it is not easy to control this pressure because of the foam of the liquid, of the boiling liquid foam we have here. Because since we have this foam, this vary in density, so then control the bottom level here. Here we usually have a control of a level. This control is inaccurate because this density changes a lot with the pressure, so the control is not very good, and we cannot ensure that the column is and the reboiler are working properly. We prefer to have this type of reboilers in systems where the pressure is high enough, let's say, that the density does not vary a lot, and we can control good the bottom of the column.
Okay, thank you.
You're welcome.
شباب أحد عنده سؤال أو استفسار عن natural circulation قبل ما نروح على forced circulation. Okay, I think you can proceed with the things.
Okay. So now let's gonna talk about the forced circulation. They can be vertical and horizontal. Forced circulation reboilers are similar to vertical and horizontal thermosiphon reboilers, except the pump is used for the circulation of the liquid rather than relying on natural or thermosiphon circulation. So here we have the liquid, the liquid from the column pumped into our reboiler, where they are usually designed to operate liquid full, and flushing occurs as the liquid crosses the control valve, which is located close to the column shell. They offer great operational flexibility, and the footprint is small. Flexibility, it means that for large operational modes, also for startup, for teardown, where we change the flow rate constantly, they operate very well because they are not operating on thermosiphon way, on thermosiphon phenomenon, but with the force of the pump. So since the liquid is pumped, it is better to control and to have a better operational flexibility. And also the footprint is small than kettle or horizontal, for vertical than horizontal thermosiphon. But of course, we have to take in our mind that we have to have enough space to place the pump. The main use of forced flow reboilers is in services with severe fouling problems or highly viscous, greater than 20, usually with more than 25 centipoise, we are going always with forced circulation. For which kettle and thermosiphon reboilers are not well suited. For services with severe fouling problems, we use the forced circulation because with the pump we can achieve higher velocities and then we can decrease the fouling problems. So the main advantages of forced circulation reboiler are good circulation, resulting in good heat transfer and reduced fouling. There is less likelihood of instabilities than natural circulation thermosiphon. Small diameter pipework can be used than for thermosiphon boiler because since we are using a pump, we have enough pressure to pump our fluid from the column to the reboiler and from the reboiler to the column. So then it's like not that we do not care, but the pipe diameter can be smaller because we can have higher delta P because it is compensated with the pump actually. And the exchanger does not need to be located close to the column, and there is no need for the column to be above the boiler because we are not working as a thermosiphon, but we have a pump who pumps our fluid into the reboiler. And the main drawbacks of forced circulation reboiler are that a pump is required. So then this is like an extra cost, another piece of equipment. and the boiler does not contribute a full theoretical stage to the separation. So this is, yes, this is the last exchanger, the last part of the reboilers classification, the first circulation reboiler. If you have any question, please do not hesitate.
Any questions, guys, on the circulation, vertical and horizontal?
العفو استاذ احمد اذا كنت توضيح.
تفضل شيخ.
استاذ احمد
يعني
استاذ شو المقصود هنا فوت برنت؟
فوت برنت المكان اللي تشغل الحيز اللي يشغل الريبويلر.
تمام، شكرا. يعني ايش المقصود؟
اي بالمساحه يعني. اوكي.
أستاذ.
اي تفضلي ست.
بلي أستاذ point 2 بالأدفانتج.
بلي.
there is less likelihood. الأرجحية بشنو ممكن يعني؟
less likelihood of instability.
بلي.
natural circulation thermocycling، يعني عملية السيطرة في انتقال السائل للريبويلر هذه راح تكون ستيبل بالفورس. ليش؟ لأن عندنا مضخة، بينما هناك يعني أي متغيرات قد تأثر على مستوى ارتفاع عمود السائل. يعني هذا
لأن ماكو مضخة هناك؟
مضخة بالضبط، تعتمدين على ستاتيك هيد.
بلي.
Okay, Olga, I think you can proceed. Thanks.
Okay. So the fourth point of the presentation is regarding reboiler type selection. So which are the factors influencing reboiler type selection? Designing and choosing the correct type of reboiler, we need to have some parameters in our mind to select the correct type of reboiler. So the first one is the fouling. High fouling fluids are located on the tube side because it is easier to clean than the shell side. Then we will want a reboiler where the boiling fluid is located inside the tubes, so we cannot consider here horizontal reboiler or kettle. So for fluids highly fueled, we will go for vertical reboilers because the boiling fluid is located inside the tube side. Also, another very important parameter is the corrosion. Corrosion issues may dictate the use of expensive alloys on tube side or shell side. So therefore, these fluids are placed inside the tubes in order to save the cost of an alloy shell. Since the fluid is located inside the tubes, there is no need to have an alloy, a shell in alloy. So in this case, it's the same as for fouling. These fluids with corrosion problems or fouling problems, we will want to place them inside the tubes. So then we will go for vertical thermosiphon reboilers. Another parameter we consider is the pressure. High pressure fluids are placed on tube side to avoid the expense of thick-walled shells. The fourth parameter we consider is the temperature. Very hot fluids are placed also inside the tubes to reduce shell costs. the lower stress limits at high temperatures affect shell design the same as high pressure. It means that high pressure and high temperature, we have the impact is, if we have this fluid on the shell side, the impact will be on the construction of the shell. So since the shell, the shell material is in comparison with the tube material is higher, we have more tones of shell than on tube side. So we want to avoid this extra cost of shell construction. So we try to place these fluids inside the tubes. And the last one, the fifth point, is the space constraints. The allowable space can dictate the use of vertical, horizontal, or internal reboiler. So regarding reboiler selection, in the following scheme, you can see a quick approach of which type of reboiler is better to consider according to some parameters. This is just a start, just a range of ideas when it's a brainstorm, when we start designing a thermosiphon. This is just a quick approach of what we can start considering. This scheme considers which is the vaporization rate we want to have. If it's above 30, or it can be also 35, since it is the maximum. Also the process fluid characteristics, for example, the viscosity, and also which is the estimated area, or if there is a bottom pump that we can use. So how can we use this scheme we see here? We could start and ask ourselves if our vapor ratio is higher than 30%. If this is higher than 30%, and viscosity, and we have a low viscosity, then we ask if our area is big, and if our area is big, we will go for kettle reboiler. However, if vapor ratio is lower than 30%, we will ask if there is a bottom pump. If we have a bottom pump, then we take a look into our fluid properties to see if the viscosity is high. Here, if it is higher again, and if yes, we can start thinking about forced circulation reboiler. If there is no bottom pump, then we have to consider, okay, our tower can be elevated. If it can't be elevated, then we have to consider horizontal thermosiphon or kettle reboiler. Or in case we can elevate this tower, we check the properties, and if we have a low viscosity and our tubes can be smaller than 6 meters, we will go for vertical thermosiphon. If we need tubes larger than 6 meters, we will go for horizontal thermosiphon because for if we have tubes too long in vertical thermosiphon, it means that we will have to elevate a little bit more the column, and this is not very likely to the cost of the plant of the elevation. And finally, no, I think yeah, we have covered all the cases. Just in this case, the horizontal thermosiphon, here we are talking also the internal reboilers are located here in horizontal thermosiphon. So that's it. This is just a quick approach of how we can start thinking about selecting the correct reboiler to our service and to our plant. And with this, we will finish the reboiler presentation. So let's gonna see